Bismillahirrahmanirrahim. This is lecture number 27. The topic is M-Aray modulation techniques. In particular, we will talk about MPSK, and my name is Muhammad Kaleem. The lecture outline comprises of multi-array, means multi-level digital modulation techniques. We will compare BPSK versus MPSK. We will talk about constellation diagram, two-dimensional modulation. QPSK is the transmitter side of QPSK, coherent detection, summary, and the quiz. Well, uh, the transmission power and bandwidth are very important parameters while designing any communication system. To reduce the bandwidth requirement, two or more bits are combined to form one symbol. So in any M-Array modulation, M-level signals are used to modulate the carrier. So one of the M possible symbols is transmitted during each symbol duration time Ts. So capital Ts is equal to capital TB times log base 2 times M. This is the logarithmic expression of symbol time, while linearly it can be written as Ts is equal to NTB. N is the number of bits a symbol comprises of, and capital T subscript B is the bit period. So before understanding MPSK, let's revisit BPSK, which is short for binary phase shift key. In binary phase shift key, we have only two symbols. So two important things we require. One is the number of symbols, uh, which represents either 1 or 0, and what will be the phase shift. So in case of binary, because we send only 0 or 1, so 0 or 1 can be represented with two symbols, and the number of symbols used can be calculated by this simple formula. M is equal to 2 raised power n, और n की वैल्यू अगर 1 पुट करें तो 2 raised power 1 means 2. So the number of symbols used in binary phase shift key is 2. Or the second parameter important we require is the phase shift between these two symbols. That can be calculated using this simple formula. So phase shift of BPSK is equal to 2 pi divided by M. So in case of BPSK, the M की वैल्यू क्या है 2 है, तो जब 2 पे डिवाइड करेंगे 2 pi, तो the phase difference between two symbols is 180 degree or pi. And if we continue our discussion, in case of QPSK, we have 4 symbols. How we calculate 4 symbols is, क्योंकि in QPSK we use 2 bits per symbol. So from this simple formula, plug value of n is equal to 2. So 2 raised power 2 means the value of m becomes 4. So if m is 4, then the second thing you need to know is the phase shift between these 4 symbols, which can be calculated again from this formula. We have 2 pi phase to work with. So 2 pi divided by m. M in QPSK is 4. So 2 pi by 4. So the phase shift between all these 4 symbols will be pi by 2. This diagram at the corner shows the comparison between BPSK and QPSK. So BPSK we have only 2 symbols, and it is represented in IQ coordinates. So the BPSK vectors pictures illustrates two 180 opposing vectors. So this symbol and the other symbol, the phase shift is 180 degree, and they are 180 degree opposing vectors. These vectors are also called antipodal signal sets. One is represented with phase shift 0, and 0 is represented with the phase shift of 180 degree. While in case of QPSK, we have 4 symbols and 2 bits per symbol, 2 bits per symbol as shown here. So 4 symbols, 1, 2, 3, 4. Each of these 4 symbols have pi by 2 phase shift. So there is a pi by 2 phase shift 90 degree. There is a 90-degree phase shift between these two symbols, and there is a 90-degree phase shift between these two symbols, and same 90-degree phase shift between these two symbols. Now MPSK, which stands for multi-phase shift key, there are n bits, so we have two things to work out कि m की वैल्यू कैसे निकालनी है using this simple formula. So m is based depends on कि कितनी bits थी, और उससे आपको number of symbols निकल आएंगे कि कितने symbols will be used to represent the binary data, and the phase shift between these symbols can be calculated by this simple formula 2 pi by m. So based on that, BASK, BPSK, BPSK, BFSK, and DPSK all are binary modulation techniques. Uh, these are represented using only two symbols consisting of single bit, either 1 or 0. So in case of binary amplitude shift key, we have only two amplitudes. In case of binary phase shift keying, we will have two frequencies. In case of binary phase shift key, we will have two phases are used to represent two symbols. But in contrast, in M-Aray, two or more bits are combined or grouped together to form a symbol. So symbol can be called as a waveform, could be called as a pulse as well. So one of m possible signals, S1 of t for symbol 1, S2 of t for symbol 2, S3 of t for symbol 3, all the way to Sm of t, depends कि m की value क्या है, is transmitted during symbol period time, which is Ts. So m possible waveforms will have the same amplitude and the same frequency, but will have different phases. So thus in M-Aray, the number of symbols is always greater than 2. And the number of symbols can be calculated by this formula, where n is, in case of M-Aray, always starts from 2 onwards, 2, 3, 4, 5. And m is total number of symbols or levels or signals. This table summarize overall multi-level digital modulation techniques. So if n की value 1 है, which is number of bits, then m will be 2 raised by n, means m is 2. And there are two symbols, एक symbol 0 को represent करेगा और एक symbol 1 को represent करेगा. If there are 2 bits per symbol, then value of m will becomes 2 raised by 2 is 4. So we have 4 different combinations. It means we have 4 symbols to represent the data, or 4 different waveforms. Similarly, if n is 3, then 2 raised by 3 is 8, and we will have 8 different combinations or 8 different symbols to represent our data. So in M-Array signaling, the processor accepts n source bits at a time and instructs the modulator to produce one of m is equal to 2 raised by n available waveforms. Means in case of n is equal to 1, the processor will accept one bit at a time and produce one of two symbols. In case of n is equal to 2, processor will take 2 bits at a time and produce one of these 4 symbols. In case of n is equal to 3, the processor will take 3 bits at a time and produce one of these 8 available symbols to represent one of these conditions. So based on the type of modulations used, M-Array techniques can be classified as M-Array amplitude shift key, M-Array phase shift key, M-Array frequency shift key, and the last is M-Array amplitude and phase shift key, which is also called QAM. QAM we will discuss in detail in the next lecture, but keep in mind if it is amplitude shift key, then we keep the phase and frequency constant, while in phase shift key we keep the amplitude and frequency constant, and in frequency we keep the amplitude and phase constant. While QAM we have two variables to represent the data. So we used to work with bit length previously in case of binary communications or binary modulation techniques. Now we have a new parameter which is called symbol length or symbol period. In some books it use capital T, some books use T subscript S. So this blue line is basically shows the length of the symbol, and in this symbol there are 3 bits, so 101, so one symbol is representing 3 bits. And that's why it is very bandwidth efficient. So bandwidth requirement reduces 3 times or 1/3 factor. Phase shifts is equal to so in any M-Array, the phase shift between any symbols can be calculated with this simple formula, and the number of symbols used can be found using this formula. The following diagram shows the comparison, graphically shows the comparison between binary BPSK and the QPSK, which is 4PSK, 4 phase shift key. So if I have a binary data 01010001 and I'm using a bipolar line code, so 0 is presented with -1 voltage. So you can see the black color shows one waveform or one symbol, and then there is abrupt change at the symbol transition time, and because it's binary the phase shift will be pi degree, 180 degree. So the next symbol or wave is generated at 180 degree phase shift to represent 1, and then again at the symbol transition time there is abrupt frequency phase change, and again 180 degree to represent symbol 1 again, because in binary we have only two symbols, so two colors are used. One is for symbol 0 and the one is for symbol when you transmitting 1. But in contrast, if you see QPSK, 2 bits per symbol, so 2 bits makes one symbol, so you have 4 different colors showing 4 symbols being transmitted, and at the symbol transition time you will see the phase shift, abrupt phase shift, and in case of QPSK using this formula you know the phase shift will be pi by 2, 90 degree phase shift. और फिर अगला symbol transmit हुआ जो कि comprises of 2 bits, and then at the end of the symbol transition time the third symbol is transmitted with a different color and having a abrupt phase shift of 90 degree, and the last one likely. So general mathematical expression of MPSK can be written as SI of t, which is a equation for ith symbol, say for instance, and it is square root 2es capital T. Es short for is it represents the basically energy of the pulse or the symbol, and T is the time duration where it lasts or time period of the symbol, and this is a typical sinusoidal wave cos 2 pi f naught t plus phi I of t, which lasts between 0 and capital T. So phi I of t is the carrier phase, which may changes abruptly at the beginning of each single interval. So that represents a constant envelope, and that's why the the threshold level in uh, MPSK is always 0. We keep it 0. So phi I of t can be expressed as, which is the phase shift between two symbols. इसको generally इस equation से represent करते हैं हम. Simple equation was shown before. If I see, this is a simple equation which tells you the phase shift between any two phases. While this is a general equation, phi I of t is equal to 2 pi I minus 1 over m plus constant, where I is equal to 1, could be 2, could be 3, all the way to m. Yes, like I said, it represents the in symbol energy. T represents the symbol time period. And at the lower, it shows two symbols in case of BPSK. So S naught of T shows the symbol 1 equation for symbol 1, and S1 of T is the equation or wave equation for the symbol 2, where theta 1 and theta 2, the difference is pi in case of binary. And you could see one wave or one symbol, and then there's abrupt change in the phase of the symbol, and then another symbol is transmitted. And this is shows the constellation of that. As uh, BPSK, the antipodal case, the BPS is basically is a case of antipodal. Only a single basis function is required to represent two symbols, S1 and S2. Now we know the general equation of MPSK is SI of t is square root 2 ES over t cos omega naught t minus, this is the theta I, which is our phase, and it lasts or exists between 0 and capital T. Now, if one wonders where this 2e over t square root 2e over t comes from, so let's see the derivation. This equation can be written as simply S of t is equal to a cos omega t, where a is the peak amplitude of the sinusoidal wave. So since the peak value of the sinusoidal wave equals square root 2 times the RMS value, so we can rewrite this equation as S of t is equal to square root 2 a RMS cos omega t. Now I can rewrite this equation again in terms of this. I'm just extending the square root by taking a square RMS. And now if I assume the signal to be a voltage signal or current signal, then a square RMS represents the average power normalized to 1 ohm. So this whole term a square RMS can be written as P, which is the power of a signal. So S of t is equal to square root 2p cos omega t. And अगर पावर को मैं एनर्जी की टर्म्स में यूज करूं, वर्क डन पर यूनिट टाइम और एनर्जी पर यूनिट टाइम, then that is equal to 2e over t cos omega t. So that's where this 2e over t comes in this equation, which is also called wavelength amplitude coefficient. Now we were talking about QPSK. There are two variants of QPSK, and we will explain how these two variants of QPSK exist. So we start with our general equation SI of t for the ith symbol, say for instance, and we know that the number of symbols उनके दरमियान जो phase difference होगा, that can be calculated by this simple equation, or number of symbols can be calculated from this equation. लेकिन अगर आप चाहते हैं कि आप हर एक सिंबल का अपना एक फेज उसका कितना होगा विद रिस्पेक्ट टू द adjacent symbol, then you could use this equation. Phi I of t is equal to 2 pi I minus 1 divided by m plus constant. So for example, in case of QPSK, अगर हमें पता है कि m की वैल्यू 4 होती है क्योंकि 2 बिट्स पर सिंबल हम रिप्रेजेंट करते हैं, और अगर मैं कांस्टेंट c जो है ये 0 रखूं, then the force phases I calculate is 0, क्योंकि अगर मैं I की वैल्यू 1 रखता हूं तो 1 minus 1 ये इस टर्म 0 हो जाएगी and that will make the whole term 0. So the first symbol will be transmitted using phase 0. If I put I is equal to 2, then this ब्रैकेट के अंदर जो वैल्यू होगी वो 1 हो जाएगी और 2 pi divided by 4 give me pi by 2. So the second symbol will be transmitted at 90 degree. And the third symbol किस phase shift पे भेजा जाएगा? I can calculate. If I put I is equal to 3, then 3 minus 1 is 2. So that will become 3 pi by 2. So using this equation, इस इक्वेशन से तो आपको सिर्फ ये पता चलता है कि फेज शिफ्ट बिटवीन सिंबल्स क्या होगा. ये इक्वेशन एग्जैक्टली बताती है कि हर एक सिंबल का फेज क्या होगा, एग्जैक्ट फेज क्या होगा. It's not just the difference between the phases of different symbols, but exact phase किस phase पे आप वो symbol या sinusoidal wave generate करेंगे. और अगर मैं इस कांस्टेंट की सेकंड, दिस इज आवर फर्स्ट केस, इन सेकंड केस अगर मैं कांस्टेंट की वैल्यू पाई बाय 4 रख देता हूँ, पहले इसको मैंने c को 0 कर दिया था कांस्टेंट, और अगर मैं इसकी वैल्यू कांस्टेंट की पाई बाय 4 रखता हूँ in second case, then I come up with the second type of QPSK. Then the four phases are, so पहले केस में यहाँ पे 0 था, क्योंकि C भी 0 था, तो यहाँ पे अगर मैं पाई बाय 4 रखता हूँ तो फर्स्ट जो फेज है जो सिंबल 1 लेके जाएगा या जिस पे वो ट्रांसमिट होगा, दैट विल बी पाई बाय 4. सेकंड इज पाई बाय 4 प्लस आई की वैल्यू 1 डाली तो दिस बिकम्स पाई बाय 2 पहले केस में, उसमें पाई बाय 4 प्लस ऐड करूंगा तो द आंसर विल बिकम 3 पाई बाय 4 आ जाएगा. एंड एग्जैक्टली फॉर द थर्ड सिंबल, पहली केस में पाई था, अगर उसमें प्लस पाई बाय 4 ऐड करूं तो आंसर विल बी 5 पाई बाय 4. एंड लाइकवाइज इफ जो पहले केस में जो सी 0 करने से जो वैल्यू आई थी 3 पाई बाय 2, उसमें अगर पाई बाय 4 मैं ऐड कर दूं तो आंसर विल बिकम 7 पाई बाय 4. सो आई हैव टू implementations of QPSK based on this equation using कांस्टेंट फर्स्ट केस में 0 और दूसरे केस में मैं कांस्टेंट अगर पाई बाय 4 रखता हूँ. सो दिस इज माय इक्वेशन इन द सेकंड केस कि मैंने ये एम्पलीट्यूड कोफिशिएंट है and the rest of the equation is same, but I am just using plus pi by 4 instead of using c as 0. So based on this equation, the first symbol is transmitted at 45 degree, which is pi by 4. और अगर आप देखें तो it is representing 2 bits. और at the symbol transition time, there is an abrupt change of, because it's a quadrature phase shift, so the phase shift between two symbols will be 90 degree. So 90 degree phase shift पे मैं दूसरा symbol transmit करूँगा और that will be at 135 degree. So the difference between 45 and 35 is 90 degree. और फिर दूसरा symbol again comprises of 2 bits, and then at the symbol transition time I will have again 90 degree phase shift, and I will transmit my third symbol or third signal or waveform, कुछ भी कह सकते हो आप, and it is 90 degree shifted from this symbol. And similarly the last symbol will be transmitted at 315, which is 90 degree shifted from the previous symbol, and it is representing 2 bits. If we see the graphical representation of these four symbols of this represents the case 1 implementation of QPSK. So 0 एंगल पे फर्स्ट सिंबल गया, 90 डिग्री एंगल पे दूसरा सिंबल, 180 डिग्री पे थर्ड सिंबल एंड 270 पे फोर्थ सिंबल. If I use the second case, then I have the first symbol transmitted at 45 degree, the second is transmitted at 135 degree, third symbol is transmitted at 225 degree, and the fourth symbol is transmitted at 315 degree. So these are two different variants of QPSK. Now let's look at the constellation diagram. Constellation diagram is basically represents a it is a graphical representation of a digitally modulated signal. This diagram helps us to define the amplitude and phase of a signal. So the signal constellation consists of m equally spaced points on a circle. So all these points are equally spaced. You need two things in order to draw a constellation diagram. एक तो आपको distance चाहिए, distance of the point from the origin. This is your origin, और इस origin से आपका जो point है उसका distance, that's the distance. In this case is ES square root, and the phase difference between the symbols, which can be calculated as we were doing it previously. So two things are required in order to understand the constellation diagram. So in case of BPSK, the vector picture illustrates the two 180 degree opposing vectors. These vectors are also called antipodal signal sets. So one can see one is represented with EB and 0 is represented with minus EB, and the phase shift between these two symbols is 180 degree. And you need only one basis function to represent that. And keep in mind, because it's BPSK, 1 bit per symbol, so we talk about bit energy EB. But if we talk about QPSK, where m is larger than 2, then we will talking about symbol energy, as we are talking about symbol time period. So if m is 4, it means there will be 4 symbols, and this is S1, S2, S3, S4, 4 symbols, and the phase shift between any two symbols will be 90 degree. And if we talk about 8 PSK, जहाँ पे value m की 8 है, तो we will have 8 symbols. In other words, 1, 2, 3, 4, 5, 6, 7, 8, and the phase shift between any two symbols will be pi by 4, and it represents 3 bits per symbol. So any signal waveform can be represented as vector having vector length. Vector length is basically the distance from the origin to the point, and the vector direction, which is the phase difference between two symbols. Likewise, constellation diagram can be used to represent any digital modulated signal or digital modulation scheme. In case of 16 PSK, we will have 16 m की value 16 होगी, तो 16 symbols will be equally spaced in a circle, and the phase shift between the symbols will be pi by 8. Now let's look at the implementation of QPSK. We will see the transmitter side, क्योंकि QPSK में m जो है वो 4 है, तो we will be generating 4 symbols or 4 signals or 4 waveforms. So QPSK signal can be generated as the sum of two BPSK signals with phase quadrature, means 90-degree phase shift. So this is also called IQ, in phase and quadrature phase modulation technique, because summing I in phase and quadrature phase signals that are either inverted or non-inverted results in four different phase shifts. Let's look at the diagram. The transmitter side, RB is the bit stream coming in, input to the bit splitter. So a binary data stream is split into the in phase and quadrature phase components. These are then separately modulated onto two orthogonal basis functions. In this implementation, two sinusoidals are used. Afterwards, the two signals are superimposed and resulting signal is the QPSK signal. So one can see that it is the factor of 2 basically is the power is divided equally between in phase and quadrature phase legs or channels, and we have two carriers or sinusoidals which are multiplied with these incoming to produce in phase component and quadrature components, and we sum them and pass it to band pass filter to generate our QPSK signal. So because QPSK signal we have four symbols, so this is the equation for the first symbol. S notes भी कह सकते हैं आप, S1 भी कह सकते हैं. So S note से अगर start किया तो S note is equal to 2ES over TS, square root 2ES over TS times cos omega CT. So this is using 0 degree. Phase shift is 0 पे हमने पहला symbol भेजा. उसके बाद क्योंकि phase shift between the two symbols is 90 degrees, so the next symbol S1 is transmitted at plus pi by 2, 90 degree. We know that cos 90 is 0. So in term, and then after working cos omega t pi by pi over 2, हम इसको अगर साइन की फॉर्म में लिखेंगे तो नेगेटिव साइन आ जाएगा इस पे, ठीक है. And then the third symbol S2 is 90 degree different from the second symbol. So there's a 90 degree phase shift between these two symbols, S0 and S1. And likewise, there's a 90 degree phase shift between S1 and S2. So plus pi page the third symbol will be transmitted or generated. और अगर इसको सॉल्व करें हम तो cos pi जो है वो 0 होता है. Cos pi is -1, sorry. So cos pi is -1 and you come up with this equation. That's why the minus comes in. And the fourth symbol, which is represented as S3, is again pi by 2 shifted from the last symbol. So this is 3 pi by 2, and in sign form it can be represented as 2ES over TS. So if I combine S0 and S2, so this is plus minus because S0 is प्लस में है और S2 जो है वो माइनस है, और दोनों cos omega CT waveforms. तो it comes to plus minus square root 2 ES over TS cos omega CT, or the phase shift between these two S0 and S2 is 180 degree. That's exactly what it says. Two BPSK signals with phase quadrature. And S1 and S3, again S1 is minus 2 ES over TS sine omega CT, and S3 is square root 2 ES over TS sine omega CT. So this is the second BPSK, and there is a phase shift of 180 degree between these two. So these are the four symbols generated in case of QPSK, which is like can also be generated by having two BPSK signals having quadrature phase shift. Now if we look at the receiver side, so because it's a phase shift keying we are talking about. So we the first option is coherent, even though there is a non-coherent detection is also possible. So, but here we will talk about only coherent detection. So coherent detection requires the phase information. So a coherent detector operates by mixing the incoming data signal with the locally generated carrier reference. So R of T is our incoming data, and this is a local oscillator which has the phase information exactly what was transmitted at the transmitting side. We multiply both signals and pass it to the low pass filter to get rid of higher frequencies, and we get z of t a sampled value at t is equal to capital T, and we compare z of t against a set reference. Normally it is set to 0, and if the z of t is larger than the reference set reference or threshold, then hypothesis h1 is true, means s1 is transmitted. Otherwise h2 is true, means symbol 2 is transmitted. So so multiplying r of t by receiver local oscillator a cos omega ct yields a signal with a baseband component plus a component at higher frequency 2fc. So low pass filter will get rid of that frequency, and we will get over z of t, which will pass through a decision statistics. We already learned this. We could use match filter at the receiver. So to detect our incoming signal, match filter can be implemented uh, or realized as the mirror image and delayed version of S of t. Or again, we have Z of t. We get a sample value at t is equal to capital T and compare with our threshold, set threshold, and see the hypothesis H1 is true or H2 is true, and based on that we detect over 1 and zeros. Now look at the coherent reduction of QPSK. Previously we were looking at the BPSK. So QPSK is like at the transmitter side we know two BPSK signals, and likewise at the receiver side QPSK receiver is composed of two BPSK receivers as well. So one that locks onto the sine carrier and the other that locks onto the cos carrier. Receiver side coherent reduction can be implemented either using match filter or can also be used or can be realized using a correlator. So both solutions are mentioned, and these two solutions were discussed in the previous lecture as well. Uh, so these are two basis functions, psi1 of t, psi2 of t, because it's a quadrature of this in phase and quadrature phase, and wave equation can be written as z1 of t as integrals from 0 to capital T s1 of t psi1 of t dt. और अगर आप s1 of t की वैल्यू डाल दें जो कि हमने पिछले इक्वेशन देखी है उसकी, और psi1 of t is this one, बेसिस फंक्शन उसकी उसकी वैल्यू को प्लग इन कर दें, then we integrate over 0 to t, we get es, which is the symbol energy, which means one being transmitted, and the other case is again s1 of t psi2 of t, and if you put the values inside and equate it over 0 t and put the values of cos omega t and sin omega t for a particular phase, you get 0. So 1 and 0 being received at the receiver side. In case of M-Aray, we could use bank of correlators, and this circuit was also discussed before to detect different symbols. So M की जो भी value होगी उतने आप correlator लगाओ, bank of correlators, to detect your M-Aray signals. Now, these are few advantages and disadvantages of M-Array techniques. QPSK uses constant envelope, so it is immune to noise. The second is considerable reduction in the bandwidth requirement in case of M-Array techniques. Increase in probability of error with increase in the number of bits per symbol. The last one is design of M-Array PSK modulator and demodulator is little complex as compared to binary. A small quiz. As the number of level increases, m value of m increases, the phase difference between adjacent symbols increase करेगा या decrease करेगा. Second is as m increases, the bandwidth efficiency of M-Array PSK increase or decrease. And the third is as the number of level increases, the probability of error increases or decreases in the number of bits per symbol. So think about it and we will discuss in the lecture. So let's see the summary. We had a bit of introduction of M-Array multi-level digital modulation techniques. In particular, we talk about MPSK and then we compare binary shift key with respect to MPSK. We look at the constellation diagram. Then we saw QPSK in details, two versions of that, and the receiver side based on coherent deduction, the overall summary, and the quiz. Thank you.